Authored by a veteran chemistry teacher, Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up, and don't forget to subscribe. We will see you in the next video, and thank you for watching.
Our lesson today discusses the factors that affect the solubility of a solute in a solvent. It starts on page 228 and it ends on page 236 from the text Chemistry 11 in Focus. And some of the things we'll be talking about will be definition of solubility, force of attraction between particles of a solute, force of attraction between solid particles and solvent particles, solubility and saturation, temperature and solubility. I have a little write-up here that I have. If every solvent on earth were to dissolve every solute, then everything will be in the form of one solution or another. But the natural order of the world in terms of solubility dictates that only specific solvents dissolve specific solutes, such as gases and solids. The selective nature of water in dissolving only some types of substances is attributed to its unique property, it being a polar molecule and a liquid. These properties allow the water in our bodies to transport dissolved waste and nutrients without dissolving structures such as our cell membranes and bones. The relative abundance of water imposes special physiological adaptations in organisms in terms of what types of excretory substances to produce. Aquatic organisms, which enjoy an unlimited supply of water, produce the very water-soluble ammonia as their main excretory product. Ammonia, being very soluble in water, dissolves well in tissues and tissue fluids of organisms. Lots of water, therefore, is needed to wash it away from their tissues. Terrestrial organisms, having to contend with less available water, produce the less soluble urea and uric acid as their main excretory products. These substances, being less soluble, require less water to be excreted. These facts show that not all substances have the same solubility in water. Kidney stones and gallstones form because these compounds from which they are formed are sparingly soluble in aqueous solution. These compounds form saturated solutions and crystallize out of solutions as stones. This chapter explains why some solutes are more soluble than others in water, and how temperature affects their solubilities. If anyone hasn't seen video 24, I beseech you to do so, since what is taught in it is prerequisite to learning well what will be taught today. So we'll be looking at factors that affect the solubility of substances. For those of you who looked at video 24, you can recall that for a solute to dissolve in a solvent, there must be some type of attraction between the particles of a solute and solvent. For example, what we saw was that water molecules and the ions in sodium chloride crystals attract each other so that it causes sodium chloride crystals to dissolve in water. What we're saying here is this: the relative ease with which the particles of a solute separate from each other and mix with solvent particles determines the solubility of the solute in that particular solvent. At any particular temperature, the solubility of a solute will depend on a number of factors. One, it depends on the force of attraction between particles of the solute. Why is it that sugar can be dissolved so easily by water. The reason for that is because the molecules in the sugar crystals are held together by weak London dispersion forces and some small dipole forces too. And water being polar is able to separate with relative ease the molecules in that crystal of sugar. And that is why sugar dissolves relatively easy in water, right? Now, what about ionic crystals now? We return to Coulomb's law because depending on which ionic crystal you're talking about, the relative ease with which they will dissolve in water or the difficulty with which they will dissolve in water depends on the ions that are present and the charges on them. What Coulomb is saying in his law is that the force of attraction between two oppositely charged species, it can be on anything, and their charges are positive or negative, is proportional to the product of the magnitude of the charges, but is inversely proportional to the distance squared. If these charges become greater and greater, it means that the force between them will be greater. But if you increase the distance, the force of attraction with them will decrease, and we did that already, a quick review of that. So here you have two ions, oppositely charged ions, and they are attracted each other by force F1, and that's the distance there. If we now double the charges, you are making Q1 and Q2 bigger now, right? And obviously, this force of attraction here will be greater than in this case. So you say that F3 is greater than F1 by virtue of the larger charges on the ions. Secondly, if we separate them farther away from each other, D2 is greater than D1, based on the equation there and based on experiences too. If these are magnets and you move them away from each other, you find that the force of attraction between North Pole and South Pole gets weaker because, they're similar to electric charges. So here's D now. So if you increase this guy here, for mathematics, that guy will get small. So here now we'll say, if we compare that force there with this force here, we see that F1 is greater than F2 by virtue of larger distance, okay? So that sets the background for us to talk about the stability of ionic crystals with respect to the types of ions that they have in the crystal. Q1 here and Q2 are the charges in coulombs. D is inter-ionic distance. So what is D? D is really the sum of the ionic radii of the two ions. So here is one ionic radius here, and that's the other ionic radius. When you add these together, you get that D here. So this is that D here. And F, of course, F is the force of attraction between these two ions. I'm going to give you to read this. So you want me to read it? I'm not the best reader. I'm going to read it, okay? Excuse me if I slip up. I'm not going to read it. The solubility of ionic compounds in water depends on the relative forces of attraction between the oppositely charged ion in the crystal. If the ionic charges are small and the distances between them are large, then according to Coulomb's law, their forces of attraction are relatively weak and the compound dissolve with relative ease in water. Cesium chloride, for example, is more soluble in water than sodium chloride is at the same temperature. Look, cesium chloride has a solubility of 1,865 grams per liter, and sodium chloride is only that 357 grams at 25 degrees Celsius. Now look now, if you look at the ions now, the ions in both compounds have the same magnitude of charge. What does it mean? This is one positive, that's one negative. One positive, one negative. Q1 and Q2 are the same in both cases. But look what happens. The ionic radius of cesium is larger than that of sodium. So see this one here? The ionic radius here? Is larger than this. The forces of attraction between cesium ion and the chloride ion are weaker than the force of attraction between the sodium ions and the chloride ions. Why? So we are saying in this case here, look, this distance here, d1 is greater than this. Or we can say this distance here is smaller than that. That's why if you go back to Coulomb's law, the force of attraction here is greater than inside. So that makes the crystal lattice of cesium chloride less stable than sodium chloride. In other words, these guys are not attracting each other so strongly. Therefore, the water molecules will be able to pluck these out of solution with relative ease than will happen here. For that reason, cesium chloride will be more soluble than sodium chloride. All right. Now another thing happens here. We show a different story, but look what happens. Now we're changing the charges, okay? Here is calcium oxide, and here you have cesium chloride again, right? Two things are happening here. Here you're having a different charges. Q1 and Q2 are different now. Here you have 2 and 2, and here you have 1 and 1. Right away you should know that the force here is going to be greater than inside there by virtue of the charges there. Not only that, look, the interionic distance here is smaller than over here. So two factors will make the force of attraction between the calcium ion and the oxide ion greater than in this one. One, bigger charges, bigger Q1 and Q2, smaller distance. And therefore, you'll expect a crystal of calcium oxide to be much more stable than that of cesium oxide. So what will happen? This one will have a greater solubility than this one. But it is that the solubility of calcium chloride at 25 degrees Celsius, 1.2 grams per liter. So I hope you understand the two factors that are responsible for making some crystals more soluble in water than others. The interionic distance between the ions in the crystals, and also the charges on the ions there, and of course the way they're packed inside the crystals, some they call the crystal lattice too. So the question is, why does ethanol dissolve iodine but not sodium chloride? Why, if you took some ethanol, you want to make a tincture of iodine, you use ethanol, and you quickly see the solution become dark brown. But if you took some sodium chloride and you try to dissolve it with ethanol, nothing will happen. Iodine's nonpolar molecules are held by relatively weak London dispersion forces. Ethanol molecules are held by both London dispersion forces and a little bit of hydrogen bonding. So to separate the iodine molecules from the crystal will not be a big deal for ethanol, because you're removing molecules that are held by very weak forces. If you try that out with, say, sodium chloride crystals, it will not happen, because the forces of attraction between the sodium ions and the chloride ions within the crystal are too strong for the ethanol molecules to separate them. So it can be concluded, therefore, that for any solute to be dissolved by a solvent, for that to happen, the force of attraction between the solvent and the solid particles must be greater than the force of attraction between the solutes. Okay? Now we talk about solubility and saturation. If you are a regular user of honey, you must have noticed that a jar of honey will crystallize during the winter, but not during the summer. This has to do with the different solubilities of solutes in water at different temperatures. So look at this example here. If you wanted to know, this is in a crude way, what is the solubility of potassium nitrate in water, 25 degrees Celsius, right? Let's say you have a water bath. A water bath is like, you have a container here. That's a water bath, okay? And you maintain this water bath at 25 degrees Celsius. And inside here now, you put a test tube. Let's say you take a test tube with 10 milliliters of water there, okay? And you maintain this at 25 degrees Celsius. Now that's 10 milliliters of water. And you want to know what is solubility, say, of potassium nitrate. You can keep adding potassium nitrate and you stir, you shake, stir and shake, until you just start to see a few flakes at the bottom there, okay? If you weigh the amount of potassium nitrate that you put inside, it will be found to be 4 grams. So we're saying that at 25 degrees Celsius, the solution becomes saturated with potassium nitrate. And the maximum amount of potassium nitrate that is dissolved is 4 grams. Okay. So I'll give you some scenarios here at the bottom here. Let us say this is one of the test tubes there. You have 10 milliliters of water inside there. And you put inside there 3.5 grams of potassium nitrate. So that's dissolved inside there, okay? You have that inside, okay? What kind of solution would you call that? You have not saturated, we call this an unsaturated solution. If you drop in now that amount there, we will say it is a saturated solution based on our experience here, okay? So that is what will be in solution, that 4.0 grams will be dissolved inside here. Another guy goes now and puts inside 5 grams of potassium nitrate. We know you can only dissolve that amount at 25 degrees Celsius, right? So what will happen? Doesn't matter how much you try to dissolve that, as long as you don't want to raise the temperature, right? You're going to get some solid potassium nitrate at the bottom here, and that will be 1 gram. But the solution is still saturated, but only you have some excess potassium nitrate. Can I ask you a question? What do you think will happen with this solution here if you start to raise the temperature of that thing there? What do you think might happen? Smart? I know you said that might disappear because at a higher temperature, this 10 milliliters will dissolve a greater quantity than 4 grams of potassium nitrate. The solution now become unsaturated, because who knows whether or not you can keep putting in more potassium nitrate there at that higher temperature and it'll still not crystallize. Same thing is repeated here, except we took some real pictures of this. Here I am having a saturated solution of potassium nitrate with 4 grams of it dissolved in 10 milliliters of water at 25 degrees Celsius. What happens if you raise the temperature to 30 degrees? It becomes unsaturated because now at a higher temperature, that 10 milliliters of solution can absorb a little bit more of potassium nitrate without any crystal being formed here, right? So that's unsaturated. Okay, go back to this guy here now. Let us suppose we took this solution here and we put it in a water bath, a cold water bath, say at 20 degrees Celsius. It's a beautiful thing that happens. It starts to crystallize at 20 degrees Celsius. So what will be here? After all the crystals have settled to the bottom here, what will be left there is still a saturated solution, but it is saturated at 20 degrees Celsius. Now, again, I can ask you the same question. What will happen if you heat it back to this temperature here? All of this in front of your eyes will gradually disappear until you end up back with that saturated solution. So this is the whole concept of saturated and unsaturated solution. With few exceptions, an increase in temperature increases the solubility of solute. One of those exceptions is, I think, sodium chloride. Sodium chloride does not show an increase in solubility over a range of temperature. If it is saturated at a certain temperature, it doesn't matter how much you raise it by. It doesn't you show a flat line. Nothing. So these are some plausible explanations as to why the solubility of a solute increases with temperature. One. An increase in temperature causes the particles of the solid to gain more energy and therefore they separate farther away, making the interparticle force of attraction less. It is something you call you increase the entropy. You're not doing that now. Secondly, when you do that, the solvent molecules will gain more energy and they separate each other, like you have to break the hydrogen bonds, right? More free water molecules are there to do their job. And finally, see what happens here? When you increase the temperature, look, these are the solvated ions, okay? That's an anion here, and these are the cations surrounded by the water molecules. Spoken about that in video 24. When you increase the temperature, you're allowing these to go farther away from each other. And therefore, if you have a sodium ion and a chloride ion here, the chance of them coming together, or these ions coming together to attract each other and to recrystallize is less. However, when you cool this guy, you're allowing these ions to come closer and closer together, and if you keep cooling that, they come closer and closer until they love each other so much, they're so close to each other, hey, they form crystals, all right? Only death will do us apart, which is water.